Hi there, welcome back. Welcome to the next video in the restoration series of this Philips 461A. An 85-year-old lady, deserves a lot of attention, a lot of respect. But I got to tell you, right now, well, a little while ago, I did not feel like respecting her too much. I felt like throwing her out of the balcony because it drove me crazy trying to do the IF alignment. I had a plan for this video. This video was going to be the last in the series. I was going to, do the IF alignment, clean up the cabinet, show you the cleaning of the cabinet. I've done it already. Put this whole thing back and do a demonstration, right? No, that's not what happened. What happened is I got really bogged down with the IF alignment, adjusting the trimmers, these little trimmer caps, or those little Y-wound things. I'll show you. And it should have gone smoothly. It went everything but. The point is, I've got it done. I'll show you the results. See this video if you want to see how I got through that. I won't show you the frustrating parts. I won't show you the swearing. I won't show you the 4 hours that I spent trying to trace an oscillation problem, which is a nightmare, as anybody who's done this will know. Anyway, I'm actually happy right now. It doesn't look like it, but I'm happy right now because I got that done. So I hope you enjoyed the video, and we'll take it from there. Okay, so we're going to do the IF alignment for the radio, and I've got the instructions over here. It's really not much. It's these 4 points. Seems easy, doesn't it? But what exactly are we doing here? Let's have a look at the schematic quickly. We know we've got 2 IF transformers to adjust. Here's one, here's the other. Now, what I normally do is I do the whole chain. But this one I'm going to do as they instruct, and you'll understand why in a second. So we are going to align this IF transformer first. And they tell us to select long wave. Check. Then they tell us using a modulated signal of 128 kilocycles to the grid of L2 via a capacitor of 32,000 microfarads. That's 32 nanofarads. So what have we got? 128 kilohertz. Amplitude 1 millivolt. It can actually go slightly lower. I'm not sure how much I'm going to need. I've got a modulated signal, 30% modulation of a 400 hertz tone for a change. That's our carrier signal at the IF frequency with a modulated tone on it. I've got it going into the switched attenuator. There's a capacitor in there already. I'm not going to worry about that 32 nanofarads because I've got one in here. I've got no attenuation selected at the moment, so it's just going through. And it says connected to the grid L2. I've soldered a wire just to the grid cap in there. It's coming out here. Signal's going to the grid of L2 and to ground on the chassis, so check. I've also disconnected the audio, the speaker. I just put this in so it insulates it from the chassis because I don't want to hear the noise. And I'm taking the signal from the speaker out over here into a dummy load. The dummy load is about 6 ohms. And from the dummy load, I've got a few things going. I've got the oscilloscope connected, and I've also got the AC voltmeter. That's the one connection, and that's the other that slipped off. And our AC voltmeter is set to AC volts at about 300 millivolts range. That should be enough. So I think we're about ready, aren't we? So now they tell us to adjust C26 and then C25 to a maximum output. What they mean by maximum output is we're going to read the amplitude or measure the amplitude of that 400 hertz signal that we're sending in here, the modulated signal. And we'll be hearing it on the speaker, except we've got dummy load on there, so we're not going to be bothered with noise. We'll be measuring the amplitude of that signal on the AC voltmeter. We set the signal level as low as possible. It's got to be discernible as a tone and measurable on the meter, but as low as possible so we don't activate the AGC. And then we're supposed to adjust C26 and C25 so that our 128 kilohertz signal gets through as cleanly as possible. In other words, at the highest amplitude. So what they're telling us to do is to inject the signal here at the grid of L2, which is the grid cap. And then we have to adjust these 2 capacitors. C25, you can just see it there, and C26, it's there. They are trimmer capacitors. The coils are fixed. This is not cores that you have to screw in. It's capacitors that you have to change. Makes no difference. You're adjusting the resonant frequency of a tank circuit, 2 tank circuits in fact, 228 kilohertz, so that is the signal that gets through. Then that will get through to the detector and then ultimately through to the audio amplifier, and you'll hear it on the speaker. And we'll be measuring it across the speaker, okay? So let's focus in on here. This is a 1 tank circuit with a coil, a fixed coil. we've got a fixed capacitor there and we've got a trimmer capacitor. Now these two capacitors in parallel add up, and in conjunction with the coil they create the frequency, the resonant frequency. Now you've got to adjust that resonant frequency to 128 kilohertz. Now you can do that in one of two ways. You either adjust the inductance of the coil or the total capacitance across it. Because the coil is fixed, we're going to adjust the capacitor across it. So far so good, no problem. Same with the side, we're going to adjust that capacitor there. Now, the problem is the type of capacitor we're talking about. This is a little strange, very strange. I've seen them before. I have never tried to adjust these caps before because they are a little weird. The capacitor is actually a tube with one wire coming in from the inside and another wire which is wound around this coil. So this is the capacitor, and the way you trim it is by winding or unwinding the number of coils, less and more coils across here on this cylinder. And the reason this works as a trimming capacitor is because this tube, if we look at a cross section of it, this tube is painted or sprayed internally with a metal coating on the insides of this cylinder. This metal coating, which is all the way around the cylinder, is that guy over there. When you start putting coils of wire around it, and these coils are actually wound quite close together, you are creating another layer of metal which is in contact, or not in contact, but is separated from that metal internal coating over there by this the material of the former. So what you're doing is creating two metal plates or sheets or surfaces parallel to each other, in close proximity to each other, and therefore you've got a capacitor. Okay, there's your Y. So that's your capacitor. Now the capacitance is proportional to how much of the surface area is in contact with the other, not in contact, but is in proximity with the surface area of the other plate. So when you increase the number of turns on here, you're effectively increasing the surface area that is parallel to the internal surface area, which is fixed. So you're adjusting the amount of capacitance that you have on that coil. There is a serious problem with this radio, and I'll show you on the schematic again exactly what it is that I fear. If you look at these trimmers, there's one, there's the other. We have to find out what potential they're at. Now, if we look at this one over here, this one's going to the anode or the plate of tube 2. That should give us a hint, and the hint is that this thing is at high voltage. If you follow this line down here, this tank circuit is serving as a load between the anode, and if we followed this line down here, down here, down here, look where it goes to. It goes to B plus or B2 plus over here. So you've got about 200 and something volts on here, on this side and also on that side, because that's going to the plate and this is an inductor, so DC voltage just goes straight through. So both sides, both plates or both connections of this trimming capacitor are at high voltage, 200 and something volts. So when you're winding it, you're unwinding it or winding it to try and adjust your IF frequency, you've literally got high voltage, B plus in your hands. How that's going to be handled is something that I'm still working on. This side is slightly different. This one here, that side of the capacitor goes to that coil, goes up there, and it goes to the grid. Where does the other side go? Where's the other DC supply? Well, it comes down here, it goes to the pot. Pot doesn't have high voltage on it. It's got some. This one actually has about 14 volts on there, I've measured. But this one here is low voltage. So if you happen to touch it, you don't kill yourself, or you don't change your hairstyle. So that one isn't too difficult. C26 isn't too difficult, but C25 is a strange one. Then they tell us to use a modulated signal for a modulated signal at 128 kilohertz to the grid of L1 via the same capacitor and adjust C21 and C22 for max. Now they're telling us to connect the signal, the signal generator signal, into the grid of L1, which is over there. It gets amplified, it comes out here, goes to this IF transformer, and we adjust this capacitor C21 and this one C22 till those two resonate at 128, and we have aligned the IF frequency. But again, same problem. This one here, if we look at this line over here, that's going pretty close to ground. It goes to over there. This is actually the AGC signal, which has an AGC cap over here. So, you know, minus, I don't know, 4, 5, 6 volts. No big deal. This one, again, there's the hint. It goes to the anode of that tube. So this one here, high voltage all the way through, because if we follow this line, this line, this line, this line, there's V plus or V2 plus. It's got a resistor, another little filter cap over there. It's over here. So again, this one here has high voltage. So we're facing two death traps, that one there and that one there. And this makes me nervous, okay? But we do have to adjust it. And the reason we have to adjust it is because I've actually done a sweep of this signal. Now I'm going to adjust it with the meter using the amplitude coming out of the speaker or the dummy load as an indication. But what I did do is I fed a signal in here and I swept it from 118 to 138. So 10 kilohertz below or so to 10 kilohertz above or so. And what I found is this thing is completely misaligned. It's aligned to about 120, 121, 122. Not really aligned, actually. It's sort of all warped all over the place. And I did a screenshot of the sweep, and I'll show you the sweep at the end, how I did the sweep. Because the way to do this is I send the signal in there. I'm not modulating it now. I'm just sending a carrier signal that's adjusting or altering from 118 to 138. It goes through the 128, and what I want to see is a nice bell curve at 128, okay, coming down on the left and down on the right. And the way to detect that is to actually measure, where did I measure this? I measured at the grid, this point here, at the diode rather, one of the detector diode of grid L, of tube L3, and that gives me a DC voltage which is proportional to the strength of the signal. It works quite well. You can actually measure it quite well, but I'm going to adjust it by amplitude. So let me show you what these little capacitors look like, the scary buggers. This is them over here. 1, 2. And if I'm not mistaken, I think this is the one that's got high voltage on it. I've got the radio off. I'm crazy, not stupid. What you do is you melt the wax that's on here. There's some wax, and I've done that already on this one. And then you can unwind it. You see that? I can unwind it. And every time I unwind a little bit, I'm reducing the surface area of the metal that is, you know, parallel to the internal metal conductive surface on the inside. So I'm reducing the capacitance. Now, all these are coils up there. I don't know how many I need to take. This was just like this, and it was, you know, waxed in. So I haven't really unwound it. I can do that and put it back. But I'm going to be doing this one first to see what the result is. And if that works, and if that adjusts the IF to 128, I then have to find a way of doing this one without killing myself. And then again, when I finish this, I've got 2 more on the other side. That should be fun. That should be real fun. I'll switch the radio on, and the first thing I notice is that that 0.7 millivolts RMS is too low. Remember, we're going into the last tube, so it should have been amplified quite a bit by then. So I'm going to increase it till I get about halfway there. That's 4 millivolts. I've got that guy at mid-scale, which is a good place to adjust from. And because I've got this on dummy load, I put the oscilloscope here just to make sure we can see something. And just for peace of mind, let me make sure I know which one is hot and which one isn't. That guy there is reading 13, 14 volts. Okay, this one? Ouch, 200 and something volts. So that's the guy I've got to be really careful about. I'm going to take a piece of heat shrink tubing and just slip it over the top there to prevent touching it when I'm working on that guy there. Good, ready to go. Wow, look at that. Can you believe that that curve is possible by tuning a couple of little formers with loose wires around them, one of them carrying lethal voltages? No, I can't either. That's not what I did, but I will show you that in due course. This is the result of that second IF transformer tuning. And it is a beautiful, beautiful, perfect bell curve, centered straight on 128 kilohertz. Now, how am I doing this? Well, first of all, I've got the signal generator providing a sweep, and that sweep is centered at 128 kilohertz. It's got a span of 28 kilohertz. That means 14 kilohertz either way of 128. And the reason for that is I've got 14 gradicules on the scope, so I want each one of them to be a multiple, equal multiple, so 2 kilohertz wide. I have a linear sweep as opposed to a logarithmic sweep. And the time is 70 milliseconds. Why 70 milliseconds? Because again, I've got 14 gradicules on the scope, and I can set the scope for a time span that allows for the entire sweep to fit on the screen. So if I set that to 5 milliseconds per division, that comes to 70 milliseconds. Perfect. Now, this signal generator is producing a trigger signal, which corresponds to the start of the sweep. So start and end of the sweep is covered within one period of that sync signal. The sync signal is coming into channel 2 of the scope, and I'm using this one as a trigger. I can actually see it. I've made it invisible. If I go here and unhide the trace, you can see that square wave over there. See the square wave, the purple one or the pink one? That is the start and end of each sweep. I put it to exactly 5 milliseconds per division, so I've got the entire sweep within the screen. And I prefer to make that invisible. Now, watch what I can adjust here. Watch this. I've got full control of that particular tank circuit. This is the high voltage one. I'm going now to the low voltage one. That one adjusts the frequency, and I can center it exactly at that 128, right in the middle. It's sort of slightly lopsided, but I can twist it a little bit. And it is damn near perfect. That's perfect. Okay. And that is peaked exactly at 128. You can see that because anything below that gets cut off. That is 128, 126, 124, etc. 128, 130, 132, 134. So it's very, very even on either side of the center frequency, the IF frequency. And that was possible because I decided to make an executive decision. Let me show you what I did. That is what I have now. I replaced these little tricky buggers, removed both of them, and replaced them with 2 trimmers that I had here. I happen to have 4 of them because I need another 2 for the other side. So I replaced those here. And I also had to make some adjustments to the capacitances. Now, bear in mind that this is not original, but hey, nor is that. Nor is any resistor that I might have needed to change. So I'm not feeling too guilty about this. This thing is going to become very adjustable, very tunable. Anybody who comes in here will be able to adjust it for whatever reason. If there is a reason, if something drifts, if a tube gets changed, then it changes the alignment. They can then perfect it. This is one tank circuit here. This capacitor is in parallel with that one. That capacitor is in parallel with that one. So I tackled that one first, and I needed to make sure that I could tune to a peak and through the peak at 128 kilohertz. What I needed to do there was, because this trimmer, this particular trimmer is not ideal. This one is up to 10 picofarads, and the ones they have on the schematic, or rather on the circuit, these little guys here, are supposed to go up to about 30 picofarads. So what I did was I kept adding capacitors in parallel with that one. Remember, that's in parallel with that one anyway, so anything in parallel would just add. And I was fortunate in that I needed to add capacitance, not deduct. So I added capacitors across there till I got to the point where this 10 picofarad adjustment here made all the difference to allow it to be tuned. The actual capacitor that I put in there, and I put it behind this little trimmer, it's an NPO capacitor. and it is, I think it's 6.8 picofarads, so fairly small, okay? This one was a different story. This one actually, I found that this capacitor was too high. That trimmer goes up to 45, so that's not a problem. But this capacitor was a bit too high. So what I had to do was reduce it. And what I did was I put a 100 picofarad in series with this one, which reduces that capacitance. And then the extra 45, 0 to 45 over here, allows me to get that adjustment span. And that's what I've got. Now that, bear in mind, is the second IF. And the signal's going into the grid of the tube just before the second IF. So we haven't got the entire IF chain yet. So there's still quite a bit to do, but this thing is working fantastically. And you know what? I'm not feeling too guilty. You know why? Because this bugger, or one of these, when I was adjusting it, remember I had the heat shrink across it, over it? Well, at one point I took it off, don't remember why, and I touched this guy. So I got zapped. When I got zapped, I said, right, all bets are off. You're coming out. I'm going to put these two together in a little plastic bag, leave it in the radio. If somebody wants to get it back to original shape in the future, they can certainly do so. Let's now see what the full IF chain looks like on that on the scope. I'm going to take the signal and I'm going to feed it into the grid of the first tube, so before the first IF transformer. I have not made any adjustments to that. I'll be doing exactly the same thing there, as I did here, but I want to see where it is now. Now, the first thing I've had to do is reduce the amplitude of the signal to the minimum. I've also had to give it another 12 dB of attenuation because this thing is now going into the first tube, so it's getting amplified there as well. And then it's going through more amplification stages, so the signal has to be smaller. And the result is actually quite interesting. Now what I need to do here, I'm getting the curve on the screen, but I'm going to adjust the, this is on fine, just to get a better range. We see straight away that things are slightly different. A few things. One, it's not centered at 128 anymore. It is actually centered at, what is that, 128, 126, 124. It's centered at about 125. It's peaking at 125, and that is because the front end has not been adjusted at all, and it was lower down, as I recall. As I remember, I did the first screen capture, it was way down. So our second IF is over here. All it's doing really is attenuating the first one that's coming through. So we need to work on that first one, get that to the center, get the two to overlap, and then we'll get the perfect IF frequency alignment. Now, what you'll notice also is that it's steeper, and it should be, because this is now a dual filter. The signal's going in through the first filter and the second filter, and the two will create this effect of bringing the sides in, making them sharper. So what I need to do is I need to do exactly what I did on this one to the front end, and then we'll see what the result is. Well, welcome back. I got to tell you, this thing was a nightmare. Now, I thought it was going to be easy because I'd done the other one. So you've done one, you've done them all. This was a different story. And the reason is it had nothing to do with this side at all. When I changed these out, I had this thing coming through, as I showed you at the end of the other one. It had a pretty steep bell curve, but at 125 or 126, can't quite recall now. And I took one out. I always do that, take one side only, replace it, and then I put it back. And this thing went into crazy oscillation. And I mean serious oscillation. I couldn't get the tone through. I couldn't get anything through. And it just got worse from there. I removed everything. I removed the other side, the other capacitors. I replaced those. Couldn't get this thing going. But to cut a long story short, long story being about 4 hours of this, I finally found that the oscillation had nothing to do with this at all. It had to do with something that I'd forgotten. It actually had to do with that little piece of wire that I had coming out of that grid of that tube at the other end there. You remember when I aligned the last IF transformers or last IF coils, I had the injection of the signal going into the grid of that tube at the other end. I had soldered a little piece of wire which was sticking out, and it started when I did this. For some reason, that wire was hanging out in the air. It had to do with the orientation of the radio. It had to do with all sorts of things, because if I moved close, it would stop, and If you've gone through an isolation and an oscillation problem, you'll know what I'm talking about. It's an absolute nightmare to detect. I finally found that's what it was. So I cut that off and I've got it working. And let me show you the result. That thing is beautiful. And watch this. Straight on 128. Through 128. Peaking at 128. Now remember this is the result of two IF transformers because I'm injecting the signal at the beginning here and I'm getting it right the way out the back there. So what I can do now is I can actually change the span from 28 kilohertz to 14. So what I have here is 1 kilohertz per division, and I can now probably align it just a little bit better. I guess that's probably the best that I'm going to get. This jumps a bit. If I do a maximum, whoops, see that? It's jumping. That is my peak. That is fantastic. And of course, as I've shown you before, I can do it on the other side as well. I have got my IF alignment perfectly peaked. Better than that, sorry guys, can't do it. And now, as somebody mentioned, and obviously something I've considered, what I could do is I could remove those guys, measure the capacitance exactly, adjust these little guys outside of the circuit to the same capacitance and put it back in there. Would it be the same? No. Would it be adjustable like this one is? No. And the reason has got to do with straight capacitances. Every position that you've got here, the physical shape, the size, it all affects the capacitance, straight capacitance. So I would not be able to get that curve over there, and I'm not going to change that. That is as good as it gets. It's going to stay like that. All I need to do now, and I'm tired of this, I really am, because after 4 hours of wondering what the hell's wrong with this thing, wondering whether I'm going to have to start everything again, I want to break. So I'm going to test the reception on this, see if we've got something back, and then there's still quite a bit to do. There's the RF alignment. I've now adjusted this to 128. I'm not sure, and it had shifted from 128 to about 126 or 125. I'm wondering whether the actual RF alignments have changed as well. There's the oscillator section, the RF alignment itself, the antenna circuit, that's got to be peaked. So yeah, let's put this down, put a signal in here and see what we get. But hey, look at that. Brilliant. Okay, here we go. I've got the radio on. Medium wave. Mini whip is in there. This is late morning. Really bad time to receive medium wave, but listen to this. Tone control's working beautifully.
Amigo oyente carnicero, hay que... Pero madre mía, esto es lo que está sucediendo, ¿no? Con Putin, ¿no? O sea, si tú pones a Putin, se ve Calígula.
Es en Zaragoza, en tu Zaragoza natal.
These are all Canary Islands. One of them is actually the same station that has repeaters on the various islands, and because I'm quite far away, I pick them all up. So this is not image frequencies or anything like that.
Entonces escribe Natasha, su cabeza oscura pero rodeada de luz ha provocado.
That was medium wave. Let's try long wave. This is North Africa. Another one from North Africa, I believe. This is either RTE Ireland or BBC Radio 4.
So how can we solve this problem?
I normally don't get anything at this time of the day on this from that transmitter. And if I wait for the beep, I would have got the Porto Santo beacon. Let's try shortwave now. Definitely not a good time of day for shortwave, but I did receive there, that's on the higher frequencies, I believe. So this baby is picking up like a champ. The only things outstanding now would be the antenna circuit, the RF alignment, and obviously the oscillator alignment. I'm not sure how I'm going to do that. I'll tell you what, I'm not really worried about that for a simple reason that, the reason is that the dial plate, when I show you the dial plate, you'll see that something is shifted there. There's something wrong with that dial plate. I'm not even sure that that's the right dial plate for this because it goes off the one end and it's too close to the other. We'll get there. We'll get there. What I want to show you also is, as you can see, the speaker has been put back. I'm not sure that I mentioned that. I washed the cloth. I did not replace it. Some of this is still... Let me switch this off. I always get nervous. Some of these stains are going to stay there. But this thing was washed, put back on. The speaker has been de-rusted. It's all done. And I meant to show you all that on this video, but it's not going to happen. This thing is going on for far too long. But put it back. It's in perfect condition. This speaker is immaculate. And as I said, I will show you in the video when I show you the cleaning up of the cabinet and some of the other hardware. And, you know, once you get it to this stage, you actually forget that you spent 4 hours chasing a bloody oscillation that had to do with a small piece of wire sticking out the bottom there. Bloody hell, what a pain. One more thing I did find, which I think you might find interesting, is I found someone had messed with this. The more sharp-eyed of you might have noticed, there's actually a little blue wire here that's been cut, and it's going to there. Now, why is it cut? First of all, it's not a color thing. I've got nothing against blue. I noticed that it was in there. That was different to all these, and I noticed someone had soldered this in from the bottom of the pot to ground. Okay, it sort of made sense. That's what you expect. Most often, or very often, the bottom of the pot is connected to ground. So someone had soldered this in here. It's completely different to the usual wire. It's thinner, different color, different type of material. And then I realized I needed to check that circuit. I needed to figure out what was going on. And I realized that because this was going to ground, it was actually bypassing a whole lot of circuits on here, a lot of components on here. So this point, the bottom of the pot, is not supposed to go to ground. Someone put it to ground. And it was working, as I've showed you before. But when I decided to remove it, I thought maybe there's oscillations going on, maybe. And I removed it, and all I got was a hell of a lot more volume, more tone control, everything came back. So this thing was put in unnecessarily. I just cut it. I'm going to now desolder it, remove it correctly, and bypass whatever hack somebody had applied there. So this is it, my friends. I'm happy. I'm happy with this stage of the restoration. I'm going to stop here for now. I've got more to show you. I'm going to do the RF alignment. I'm going to do the cabinet. I've started the cabinet. I've done quite a bit of it already. It's coming out quite nicely, but I'll show you the result. I want to put all this back into the cabinet, you know, and do a final test to make sure that everything is spotless. So I do hope you've enjoyed this section. If you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon. Links at the end of the video and in the description below. Once again, thanks for watching. Bye for now and stay safe.